Alright guys, welcome back. We're going to look at Venn diagrams today, which were invented by John Venn. If you ever want to have something named after yourself, invent a diagram. So a Venn diagram is a good way of visualizing how groups break down into separate characteristics. We can see here that we've got our 10 weird looking Lego cardboard people, and we might want to categorize them by whether they've got brown hair or not, and whether they've got glasses or not. Now our first gentleman here, he does not have brown hair. He does not have glasses, so he would go outside both of those circles. Our second person does have brown hair, does not have glasses, so they'd have to go in just the brown hair but no glasses part of the circle. And you could go through the list of these people and you could put them all in the place where they belong. Now, something we can do to make this a bit easier to read is we can just count up how many people are in each group and write that down instead. So instead of drawing 3 people in the brown hair circle, we can say, oh well, there are 3 people in this part of the circle. There is 1 person on the overlap, 1 person with brown hair and with glasses. There is 2 people with glasses but no brown hair, and there are 4 people who don't have brown hair or glasses. Anyway, we can do the same sort of thing with numbers because it's unlikely they're going to give you that weird video game roster. And we might want to sort the numbers 1 to 10 into this Venn diagram. So I always feel like it's useful in this case to write everything down in case I forget one of them, which has happened. And if I'm talking about numbers that are even, I'm obviously talking 2 times table, and square, I think that's probably worth highlighting, are 1, 4 and 9. 1 squared, 2 squared and 3 squared. So go through the list. Number 1 isn't even, but it is square, so it would have to go in the square circle. Number 2 is even, but isn't square. Number 3 is not even or square, so it's going to go outside. And number 4, well, that is an even square number, so that's going to go in the middle. Then you can sort of repeat through the process. So 5 is going to go outside, 6 is going to go in even, 7 is going to go outside, 8 is going to go in even, 9 is an odd square, and 10 is even and not a square. So we could split up our 10 numbers in that way. And we could then summarize that. We could say, well, there are 4 numbers that are even but not square. There is 1 number that is even and square, 3 numbers that aren't either, and 2 numbers that are square but not even. So yeah, that's the basic idea of a Venn diagram, and I think hopefully that makes sense. So let's have a look at some examples of using Venn diagrams to find probabilities. Our first question here, we talk about a class of 30, and we're told about people that are involved in the choir, people in the band, and people that are in both. We want to put this into our Venn diagram. Now you always start with the center when you're trying to draw one of these. We've got 3 people that are involved in both band and choir, so we're going to write a 3 right in the middle, the intersection of those 2. We're then told there are 9 people that work in the band, and it might be tempting to write 9 here, but that would be wrong. The total of this entire B circle has to add up to 9. We've already got 3 people, so there are only 6 people left to account for. Similarly, it says there are 7 people involved in the choir, but we've already got 3 of them, so there's going to be 4 people in the rest of the choir circle. Lastly, there's a class of 30, so we need to take away all of these numbers that we can see, which is going to give us 17, to get the number on the outside of the Venn diagram. And the outside of the Venn diagram is still part of the diagram. It's not like optional. So we're then told to find some probabilities. We want to find the probability a student is in just one group. Now there are 6 people in just the band, 10 people in just the choir, so that's a total of 10 people. There are 30 students in total, so our probability is just 10 out of 30. If we want to know the probability a student is not in the band or the choir, well, that's just the 17 people on the outside, so that would just be 17 out of 30. So once you've drawn your Venn diagram, generally quite easy to read off the numbers that you need. Okay, let's look at a 3-way Venn diagram. We've got 100 vet visitors this time, and again we want to start with the center. The center is people that own all 3 of these animals. We've got dogs, cats and fish. So our 7 is going to go right in the middle. We then work our way outwards, so the next one we might look at is dogs and fish. There are 12 people that own dogs and fish, but we've already counted 7 of them right in the center, so the rest of the dogs fish overlap is going to be 5. 10 own cats and fish, So that means we're going to have 3 here. We've already counted 7. 15 own cats and dogs. We've already counted 7. So there are 8 left over. And then we've done basically the center, and we've done the next closest to the center. So we're now going to go to just the dog circle, just the cat circle, just the fish circle. 30 people own dogs, but we've already counted 8, 7, 5. We've already counted 20 of them. So there are only 10 left over. It's really important to count everything that's inside that circle when you're doing your subtractions. 50 people own cats. There are 18 people already accounted for, so 32 remaining cat owners. 40 people own fish. There are 15 accounted for, so that leaves 25 in the fish circle. And then finally, we've got to do the outside. There are 100 vet visitors, so we need to subtract all of these numbers from 100 to figure out what's left over. So that's 10, 18, 50, 55, 62, 65, 90. There are 10 people on the outside of this Venn diagram. So our completed diagram would look something like that. Now, we do actually have a question here. It says to find the probability does not own a dog, cat, or fish. And that's just a simple case of saying, well, there are 10 people which are outside all 3 of the circles out of 100 people who went to the vet. Okay, so this time you have to draw the Venn diagram. I'd like you to pause the video and have a go. Okay, and let's see what you got. So our Venn diagram should look something like this. You've got 2 circles, one for TV, one for laptop. We normally want to start with the middle, so we're going to write 40% in the middle. We could then look at laptops. 50% own a laptop, but we've already got 40 of them, so there's 10 left over. 70% own a TV, but there's 40 of them, so there's 30 left over. And then all that adds up to 80%, so there are 20% left over. We want to find the probability someone owns exactly one of these. That's the 30% that own a TV, the 10% that own a laptop, put them together, 40%, or 40 out of 100. Okay, this second question is slightly different in that we can't start from the center. We need to be a bit cleverer about overlaps. Again, pause it, have a go while I'm drawing this out. Okay, so the problem here is it doesn't tell us how many people read a broadsheet and a tabloid. In fact, that's the thing that we're trying to figure out. So we actually, in this rare instance, have to start from the outside because we're told 35% do not read any newspaper, and so we could put a 35 on the outside. Now we know that all of this has got to add up to 100%, so if we take that away from 100%, we'll get that these 2 middle circles have to add up to 65%. However, we're told 30% read a broadsheet, 50% read a tabloid, and if we put that together, that ends up giving us 80%. Now, there's a difference of 15% between those 2 values of the 65% they should add up to and the 80% that we've sort of got them adding up to. And the really clever thing we can do here is we can use that 15% difference, and that's what's going to be on our center. You can sort of check it works from there. 30% read a broadsheet. We've already got 15%, so that must mean 15% left over. 15% read a tabloid. There's already 15, so take that away. 35, and those 4, yeah, they add up to 100%. So you just want to look at the difference between what's left and what your 2 values add up to. Right, so let's have a look at a couple more exam questions. Again, I'd like you to pause and have a go first. Okay, going to assume you've done that. So we've got 86 teachers, 42 males, 44 females. A third of the male teachers have blue eyes. Okay, we can do something with that. There are 42 male teachers, so a third of that is just divided by 3 is 14. And we can also take that away and say, well, there are 28 that do not have blue eyes. So 14 blue and 28 not. Quarter of the female teachers have blue eyes, so again let's do a quarter of our 44 female teachers. That gives us 11 blue and 33 not. Okay, now let's actually look at the question. We want to complete a Venn diagram, so we want to put this information into this table. M is going to stand for male teachers, and B is teachers who have blue eyes. So maybe the point that we'd start with is the middle. That is people that are teachers that are male and have blue eyes. So that's our 14 that we worked out over here. We then know there are 28 people who are male but do not have blue eyes. We know there are 11 female teachers with blue eyes, so they'd have to go outside the male circle. And then there are 33 people that are not either of those things, are not male and do not have blue eyes. You could probably check this adds up to 86, 28, 42, 53, 86, yeah. So that looks like a fine Venn diagram to me. We then want to find the probability that a teacher has blue eyes. Now there are 86 teachers in total, so that's going to be on the bottom of our probability. How many of them have blue eyes? Well, that's both of these added together, the 14 and the 11. So 25 out of 86. What's the probability a teacher with blue eyes is male? So we're actually not looking at all 86 teachers here. We're looking at just teachers with blue eyes. And there are 25 of those, which we worked out before. And what's the probability that one of those is male? Well, there are 14 blue-eyed teachers who are male, so 14 out of 25. Okay, one more exam style question. Again, pause the video and have a go first, and then let's see what we come up with. So in this question, we're told there are 150 cars. We're told that basically R is going to stand for red cars and J is cars manufactured in Japan. And we want to find the probability that a car is red. And the problem is we've got this X in the question. We need to get rid of that. Now what we're going to use is the fact that all four of these numbers, the 2x plus 5, the x minus 7, the 21 and the 68, if we add those together, have to equal 150 because that's the total number of cars. And from there, it's a nice linear equation to solve. We've got 2x and x, so that's 3x in total. 5 minus 7 plus 21 and plus 68 is going to give us 1987. So 3x plus 87 is equal to 150. And then if we subtract the 87, we're going to get that 3x is equal to 63. And if we divide by 3, we'll get that x is equal to 21. Something people do wrong here is stop at that point because they've just figured out x, and that's obviously the end of any question. We still need to work out the probability a car is red. So we could fill in these values. 2x plus 25 plus 5, that's 42 plus 5, that's 47 cars. X minus 7, that's 21 minus 7, that's 14. And that should give us all the numbers we need. We could check they add up to 140, and they do. Right, find the probability that it is red. There are 150 cars, we say because we're choosing a car at random, and there are 14 plus 21, there are 35 red cars. So 35 out of 150. So hopefully so far so good. But the thing that makes Venn diagrams into a higher grade GCSE topic is the introduction of set notation. And again, this is just terminology and it's just ways of writing things with symbols instead of words, but we do need to understand exactly what's going on with it. So the first thing is obviously I should say what a set is. A set is just any list of numbers. We call the individual parts of the set the elements of the set, and we tend to write a set inside curly brackets because it looks cool. So we could have here our set A, and it has the elements 1, 2, 3, 6, 8, and 10. We also define a set B, we can also define a set C. Now the first important bit of notation here is this symbol. This is the intersection symbol, and it means things that they have in common. So if we were told A intersection B, we'd want to write down all of the elements that are both in A and in B. Now if we go through and we look at A and B, well, they both have a 3 in them, they both have a 6 in them, and they both have an 8 in them. So our set of A and B, or A intersect B, will be 3, 6, and 8. Does that make sense? So we could try and do the other two possible intersections with these sets. I'd like you to try and figure them out first. Okay, so for B and C, I think they've both got 4, 6, and 8 in common. And for A intersect C, they've both got 2, 6, and 8 in common. So hopefully you got those answers. I want to make a note here. A intersect B is often read as A and B, as in elements that are in both A and B. I think it's important to introduce that definition second, because people can get confused with that word and think it means like both of them combined. We're still talking about elements they have in common. The second important bit of notation is this symbol. Now this is a union symbol, and it means elements that are in either one of our two sets. So if we were to do A union B, we would want to write down all of the numbers that are in either set or both. So we do have a 1 because we've got one in A, we've got a 2 because there's one in A, we've got a 3 because there's one in A and B, we've got a 4 because it's in B, we've got 5 because it's in B, we've got 6 because it's in both, we've got 7 because it's in B, we've got 8 because it's in both, and we got 10 because it's in A. So the only thing that isn't in A union B is 9 in between 1 and 10. Now again, I'd like you to have a go at B union C and A union C, and then see if what you've got matches what I'm about to write down. So for B union C, we don't have a 1, but we do have everything else between 2 and 8. So 2, 3, 4, 5, 6, 7, 8. And then for A union C, we've got 1, 2, 3, 4, 6, 8, and 10. So hopefully you got those as well. Another note here, this union symbol is sometimes read as or, as in elements that are in A or B or both. The third important bit of notation, and basically the last one, is this one here. Little apostrophe looking thing, which stands for a complement, which means elements that are in a universal set that are not in this particular set. Now the universal set, I think we've already seen it on some of the previous questions. It just means, well, what are all of the numbers that we're considering in total? And in this example, we're going to say that our universal set is everything from 1 to 10. So anyway, back to this complement. If we looked at a complement, that would be all of the elements that are in 1 to 10, but are not in A. So A does have a 1, a 2, and a 3 in it, so we wouldn't have those. But it doesn't have a 4, it doesn't have a 5, a 7, or a 9. So A complement would look something like that. Again, I'd like you to pause, try and fill in the other two. And let's see what we should have. So for B complement, well, it doesn't have a 1, or a 2, or a 9, or a 10. And then lastly, A union C complement. Now that means everything that isn't in A union C. So the first thing I would work out is what is A union C. Now we did that on the previous page, but it ends up being quite a lot of numbers. And then we'd look at this list and we'd think, well, what's not in that? So our A union C complement is, well, it does have a 1, 2, 3, 4. It doesn't have a 5, or a 7, or a 9. So there we go. It looks complicated, but it's just a case of working out the thing in the brackets first and then look at the complement. Again, another way we can read a complement is not A, as in things that are not in A. So there's a little summary slide of what we've just introduced. Let's have a look at it in action. So one of the main things that you need to do with Venn diagrams then is shade them in based on what matches a certain bit of set notation. This is one of those things that looks baffling if you've never seen it before, but it's really okay. Once I've got the ball rolling on these, you might want to pause and try them yourself before I fill them in. And I'll also say you might want to shade them a little bit better than I'm going to, because I'm using sort of rubbery graphics pen. So our first one is just A, and that just means everything that is inside the A circle. So we'd want to shade in just that entire circle. Our second one is not A, and that means everything that is not in the A circle. So we would shade in this outside bit, but we'd also shade in this part of the B circle that's not in the A circle as well. Okay, what about A intersect B? So that's something that's in both of them, and the only part of the graph that's in both of those circles is this middle here. And finally, A union B, that's everything that's in A combined with everything that's in B. So we'll shade in all of the A circle and all of the B circle. These four that I've just shaded in are the four basic Venn diagrams. So if you learn nothing else from this, make sure you know this page. Let's look at some more complicated ones though. So this is a series of intersects and unions. We've got A intersect B complement. So that means we want all of the elements that are both in A and are not in B. So that would only be this part of the A circle, because we can't be in the B circle. Second one here, we've got A dash and B dash, or A complement and B complement. That means it can't be in A and it can't be in B. And the only part of the diagram that matches that is this outside of both of them combined. Third one, A union B dashed, so that's all of the A circle, so we can go ahead and shade that in, combined with everything that's not in the B circle, so we can also shade in everything that's not in the B circle. I think you're generally in luck if you've got yourself a union question, because you can just shade in the first thing and the second thing, and it doesn't really matter about overlaps. So let's do the same thing here. It says we want to shade in A dashed, so that's everything that's outside of the A circle. Union B dash, so everything that's not in the B circle as well. Okay, last four, a bit more complicated, including some brackets. Remember what I said before is that you can often think about the thing in the bracket first and then sort of reverse engineer it from there. So we're going to try and do that. So our first question is A intersect B complement. Now I think it would be really useful to quickly write down what A intersect B is, and we've done that on the first page. That's just the middle of the two. So if we want the complement of that, that'll be everything that is not in the middle. So that's all we need to shade in. Everything that's not in the middle. Again, try and do the same thing for this second question. I'm going to try and shade in A dashed intersect B. So that's everything that's in the B circle but isn't in the A circle. That's just this sort of crescent moon looking thing. And we want the complement of that. So we want everything that isn't that. So we'll shade in everything else. Okay, third question, it's a union intersect this time, but we're just going to do exactly the same thing. We're going to first say, well, what's A union B? That's all three of the circle parts combined. We did that on the first page. And we want the complement of that. So we want everything that is outside the two circles. And finally, A dashed union B dashed. Again, we want to shade that in to start with. So we want everything that is outside the A circle and everything that's in the B circle. So that's going to be everything except the left-hand part. And then we want the complement of that. So we do want that left-hand part and nothing else. Now, if that's a bit confusing, it might be worth going over them again. But you've basically seen all of the questions they can ask you with regard to shading the diagrams. Now they can ask you this the other way round. I've only done a few examples here. Again, pause, have a go, and then see if what you've got matches what I've got. Okay, let's go. So the first one is just the B circle. So the region is just B. The one underneath it, I'm going to do next, is the union of the A circle and the B circle, because it's all of the A circle and all of the B circle combined. The Third one here, that's everything that's outside the B circle. So that is just B complement. And then there's loads of ways of writing this fourth one, but I generally prefer this is the complement of A intersects the complement of B. I think another way you could have it on one of the previous pages we had was A union B complement. So let's put this all together. We've got some Venn questions to finish off, which use some set notation. So we've got people's sports that they enjoy. Obviously, people can enjoy more than one, and we've got what F, R, and H are actually defined as. We want to find the probability of F intersect R. So that's the probability that someone likes football and they like rugby. Now we know that there are 80 people, so all of these probabilities are going to be out of 80. So we just need to count how many people fit into these categories. So F intersect R, that's football and rugby. That's both of these parts here, the 31 and the 17. Put them together, we've got ourselves 48 people like both. Second question, F union H. So that's all the people that like football combined with all the people that like hockey. So we can count the 4 people here, 17, 31 and 14, because all of those are in the football circle, and also anyone who's in the hockey circle that we haven't counted yet. If we put all of those together, 28, 59, 76, well, quite a bit, 76 out of 80. Then for the third question, F dash and H dash. So that means all the people that don't like football intersected with all the people that don't like hockey. So we want the outside of the F circle combined with or intersecting the outside of the H circle. So this one person will count, this 3 people will count, and then everyone else is either someone who likes football or someone who likes hockey. So it's just 4 out of 80. So we'll have a look at 2 more questions. We're told our universal set here is all the numbers from 1 to 12. S stands for square numbers, E stands for even numbers, and we just need to complete our Venn diagram. So again, you go through the list and you fill in the numbers. Fairly straightforward, I think, for part A. For our second part, we want to find the probability of S intersect E. Remember, that's just the center part of our diagram. A mistake you could make here would be to write 4 as your amount of things in there, but remember, these are all separate numbers. There's only one number in that intersection, and there were 12 numbers in total, so just 1 out of 12. So to finish off, we've got a fairly complicated question, some bits of fractions in there as well, a bit of algebraic solving. Let's have a look at this. So we've got 150 students this time. C is for chemistry and P is for physics. We're told the probability that a physics student chosen at random studies chemistry is 5 out of 12. Now, how many students are there that study physics in total? There are x plus 35 of them, because that's this bit here and this bit here combined. How many students are there that study physics and chemistry? Well, there's just these x of them here. So another way that we could write this physics student also studies chemistry is 5 out of 12 is x out of x plus 35. Now, because those are the same thing, we can set them equal to each other. We end up with this interesting looking equation. Now, because it's maths, we're probably going to have to try and find that x. Let's try and work on that. We can do some cross multiplication here. We can times the 12 across to the left hand side, and we can times the x plus 35 across to the right hand side. Then we could expand our bracket. We could subtract our 5x, and we could divide by 7, and we'll get that x is equal to 25. Great. So we can fill in 25 in the center. We probably need the outside as well. So the 3 numbers that we've got, the 47 and the 25 and the 35, add up to 107. There are 150 students in total, so take that away from 150 and we'll get ourselves 43. So that means 43 students don't do either. Okay, let's actually look at the question. One of the 150 students is chosen at random. Find the probability doesn't study chemistry or physics. Well, that's those 43 people we've just found out of 150. So yeah, Venn diagrams. Enjoy.